In the vastness of the universe, we often gaze at the starry sky, pondering eternal and profound questions. Is the universe infinite? Is the matter within it also boundless? These questions may never find definitive answers, but in the real world, it is hard to imagine that the total amount of space and matter could reach a mathematically infinite state. Let us set aside the elusive concept of infinity for a moment and imagine this scenario. In a completely sealed room, a fresh apple rests quietly on a table. As time passes, the apple's surface softens, brown spots spread, and it eventually decays, merging into the air. Yet, given an unimaginably long period, the matter composing the apple might rearrange and reassemble into an apple identical to its original state. And this process could repeat countless times. Though seemingly impossible, this process is a profound metaphor for the interplay of finiteness and infinity. No matter how many atoms form the apple, their quantity is finite. As all atoms move in a seemingly random manner, over the infinite flow of time, all apparently disordered phenomena may return to their initial states. Isn't our universe much the same? Everything within it, including ourselves, is composed of those tiny, mysterious fundamental particles. These particles move chaotically in the endless expanse of space and time, weaving an inaudible cosmic melody. We can't help but wonder, if time stretches infinitely, will these particles rearrange themselves, reverting to the gentle states of moments past? If the answer is yes, does it mean our universe is part of an eternal cycle, endlessly repeating its beautiful and moving moments? To unravel this mystery, we must first delve into the enigma of a principle often dubbed the most despair-inducing law of physics, the Second Law of Thermodynamics. In 1865, German physicist Rudolf Clausius introduced the concept of entropy, a mysterious yardstick for measuring the disorder of the universe. In a closed, isolated system, heat always spontaneously flows from hot to cold, and the system transitions from order to disorder. This process is irreversible. Entropy always increases, like a sorrowful dirge of the universe. We can feel the relentless effects of the second law of thermodynamics in our daily lives. Take the apple, for example. From freshness to decay, from integrity to disintegration, it inevitably becomes more disordered. Or consider a cup of hot water that cools down over time, or a house that gradually deteriorates with the passage of years. All of this is a result of entropy's continual increase. Einstein even called the second law of thermodynamics the first law of science, as it governs the evolutionary processes of all life and non-life in the universe. However, this law also reveals a despairing truth. From the moment of the universe's birth, its fate was sealed to eventually head toward destruction. In the next 5 billion years, the sun will exhaust its hydrogen fuel, its core collapsing under gravity and heating up rapidly, causing its outer layers to expand dramatically and transforming it into a red giant. Its radius may extend beyond Earth's orbit, engulfing our home entirely. After another 10 billion years, the sun will evolve into a white dwarf and then gradually cool into a black dwarf, eventually falling silent. Other stars in the universe will follow similar fates. The stars in the night sky will extinguish one by one, and approximately 10 to the power of 14 years from now, with the death of the final star, the universe will plunge into eternal darkness, with no new stars being born. In this desolate darkness, black holes will dominate the universe. Their mergers will become the primary events in the cosmos. If any civilizations exist in this era, the regions around black holes will be their last sources of energy. But even black holes are not eternal. According to Stephen Hawking's theory of Hawking radiation, black holes will gradually evaporate due to quantum effects and eventually vanish. Hawking radiation, a poetic and mysterious concept based on the uncertainty principle of quantum mechanics, suggests that even in a quantum vacuum where no matter exists, pairs of virtual particles, a particle and its antiparticle, spontaneously appear and annihilate each other in fleeting balance. However, near the event horizon of a black hole, the fate of these virtual particles changes. One particle may be captured by the black hole, while the other escapes, transforming into a real particle and being emitted as radiation. This process, known as Hawking radiation, leads to a gradual decrease in the black hole's mass as the absorbed particle carries negative energy. Ultimately, the black hole completely evaporates. Although this process is extremely slow, measured in timescales of 10 to the power of 100 years, all black holes will eventually disappear. When the last black hole evaporates, the universe will be left with only photons, subatomic particles, and an ever-expanding void. The temperature will approach absolute zero, and entropy will reach its maximum. The universe will settle into a state of ultimate disorder and stillness, heat death. This grim conclusion is like the finale of a grand cosmic symphony. Is this truly the end of our universe? If humanity, surviving diseases, wars, natural disasters, and all other calamities, were to rise to the pinnacle of the universe, would we still be unable to escape extinction? Yet, within this despairing finale lies a glimmer of poetic possibility. French mathematician Henri Poincaré proposed a hopeful hypothesis. In a closed and finite system, given sufficient time, all states of matter could return to positions infinitely close to their initial configurations. This is known as Poincaré recurrence. It resembles an eternal love song, repeating beautiful moments endlessly in the cycles of the universe. Poincaré recurrence, long regarded in modern physics as a mathematical idealization, seemed difficult to verify in reality. However, in 2018, researchers from the University of Vienna published a paper titled Recurrences in an isolated quantum many-body system in Science, providing experimental support for this theory. The researchers created a closed system environment within a quantum computing setup composed of qubits and subjected it to numerous quantum state evolution processes. They found that after a period of evolution, the quantum system's state astonishingly returned to one closely resembling its initial state, despite the system's specific behaviors being intricate and random in detail. This phenomenon aligned with Poincaré recurrence theory, demonstrating that even on a quantum scale, systems could return to near-original states after a series of random changes. What is even more astonishing is that this recurrence does not merely involve simple repetition. It exhibits an extraordinarily precise periodicity on a probabilistic level. Despite the extreme uncertainty of quantum evolution, the experiment revealed that, over extremely long timescales, the system could approach a finite pattern of repetition across multiple evolutions. This experiment marked the first experimental verification of Poincaré recurrence in a quantum system, offering a new perspective on the universe's ultimate destiny. Poincaré recurrence suggests that the universe may not be a one-time event but a vast cycle. If this theory holds true, everything we experience today, our loved ones, friends, partners, choices, and memories, might have occurred in the distant past and will reoccur in the future. Every moment might become an eternal part of this grand cycle. With the experimental verification from the University of Vienna in 2018, Poincaré recurrence has transcended theoretical speculation to become a demonstrable phenomenon in the quantum world. Although this cycle surpasses human temporal scales, it provides an inspiring direction for exploring the ultimate fate of the universe. Through the poetic lens of Poincaré recurrence, the universe is no longer a cold, chaotic endpoint but a realm of endless hope and possibility. Each particle, each moment contributes to the melody of this cosmic song. And we, as part of this universe, continue to experience and cherish these beautiful, moving moments. Perhaps one day in the distant future, we will return to this familiar universe, reliving the moments that once stirred and touched our hearts. By then, we will treasure it all the more, for we will understand. Every experience is part of the eternal love song of the cosmos.